Hello and welcome to today's lesson on the Big Bang Theory, which is part of the space physics topic in GCSE Separate Science physics. So in today's lesson we're going to be looking at the Big Bang Theory and looking at understanding the formation and the evolution of our universe. So if we have been successful and learned in today's lesson, we should be able to understand what the Big Bang Theory is, understand how the universe has changed over time, and then understand what the steady state theory is and compare it to the Big Bang Theory. So in today's lesson we're going to look at the following part of the Separate Science only section of the physics specification 4.8.2 redshift. So when asked about the creation of the universe, the theory most people will mention is the Big Bang Theory. But who has heard of the Big Bang Theory, who can state the principles of the Big Bang Theory, and who can explain the principles of the Big Bang Theory? Now the Big Bang Theory is so well known and accepted today, yet it was only fully accepted by the scientific community in the 1960s. So if this lesson had taken place in the 1950s, you'd have been taught two different theories and told both were equally as likely to be true. Now this all comes from the questions asked from Edwin Hubble's work on redshift, which we've looked at in previous lessons. Now it's important that we can explain how scientists are able to use these observations to arrive at theories such as the Big Bang Theory. Now the idea of how the universe began all started with a force that physicists were fascinated with in the 1900s, gravitational attraction. Now in theory, gravitational attraction is attracting all objects closer to each other in the universe. Now physicists deduced it would mean that the universe was getting closer together and therefore smaller, as gravitational attraction was pulling every object in the universe closer and closer together. So gravitational attraction would cause the galaxies to be moving towards each other. So gravitational attraction will be causing the universe to shrink. So all galaxies in theory should be observed to be blue shifting. So they expected to observe this effect when they looked at distant galaxies. But then a scientist called Melvin Slipper looked at galaxies moving in the universe, and he realized that everything in the universe was moving apart. This went against the idea of gravitational attraction pulling the universe together, because it was observed that all galaxies were redshifting. So this shows us that the universe is increasing in size, it is expanding. So redshift is proof of the expansion of the universe. So the expansion of the universe will cause the objects to be moving further away from each other. So if the universe was expanding and getting bigger, what had it originally come from? Surely there must have been a starting point. So the Hubble's law, which is that the further a galaxy is away from us, the greater the redshift observed, so the faster it's moving away from us, meant that it allowed physicists to speculate, if all objects are moving away from each other now, were they all once condensed in one region of space? So physicists decided to investigate the mechanics of this potential expansion of the universe. Now the first person to do this was someone called Alexander Friedman. Now he was the first to realise that the universe was expanding but couldn't prove why. Now whilst Friedman is famous to physicists, the general public don't know that much of him. However, Albert Einstein realised why the universe was expanding and published his theory in 1909 called the Theory of Relativity, and became one of the most famous physicists that ever lived. So the expansion of relativity proves that the universe is and should be expanding. So by the 1950s it was understood that the universe was expanding. But what was the mechanism behind the expansion? Was there one big push at the start of the universe causing this expansion, or has there been a continuous push all the way through the universe causing this expansion? So this led to two separate theories of scientific creation developing. So you've got the steady state theory, which is that the universe had no beginning and no end, and the universe has expansion through the continuous creation of matter in the universe, and this is proposed by the physicist Fred Hoyle. Whilst the Big Bang theory is that the universe has a starting point. The universe has expansion through the point of creation and was proposed by the physicist George Gamow. So the first theory of creation that was published was the steady state theory. So the steady state theory says the universe has no beginning, it started at infinity, it has no end, it ends at infinity, and will always be expanding. So new matter is continuously created by this expansion. This means the density of matter in our universe is constant. So this postulated that the push of the expansion of the universe was happening throughout time. Now the next theory theory to be published on creation was the Big Bang theory. Now this was published by unknown Russian physicist George Gamow. Now the Big Bang theory says that the universe had a beginning and will always be expanding. So all the matter was created at the start, so the universe started as a very hot, very dense and very small region, so the matter density of the universe is currently going down. So this postulated that the push happened at the moment of creation. Now interestingly, the name the Big Bang theory was a nickname given for the theory by Hoyle. It was actually meant as an insult, because Hoyle believed that the Big Bang was a party trick, a game, not a true physics concept. So we've got our two separate theories of the creation. We've got the steady state theory and we've got the Big Bang theory. So here's a chart comparing the two theories. So you can see that in the Big Bang theory, the universe is expanding over time and the matter density in the universe is decreasing, whilst in the steady state theory, whilst the universe is expanding, the matter density is remaining constant. So in the 1960s, there were two main ideas on how the universe began. There was the Big Bang theory, the theory that the universe has a beginning, which is a very hot, a very small and very dense region, and has been expanding ever since due to matter forming at the beginning. You've also got the steady state theory, which is that the universe has no beginning, it has no end, is always expanding due to continuous matter forming. So we now believe that the Big Bang theory is the correct theory, so let's have a look at what the Big Bang theory suggests. So in the beginning, before the Big Bang, there was nothing. Time and space did not exist because Einstein proved that time is just another dimension of space, like length or width, so there was nothing to observe or reference any frame of time against. Now this is so weird and alien to understand, but don't worry about it. As humans, it's impossible for us to visualize or comprehend this. So as humans interpret nothing as black, this actually isn't the case here. There's no way you could actually physically visualize what it was like before the Big Bang. So before the Big Bang, there's nothing to consider. Now everything you can consider does not exist. So at this point, everything is fundamentally meaningless. At this point, the universe then comes into existence. Now even though we call this the Big Bang, it's not a bang, it just happens that we associate a bang with something happening and energy being released. In reality, all of matter just slipped into existence, or at one instance all of the universe appeared. So all of the matter, everything in the universe was concentrated in an area smaller than one atom, which again is really difficult to imagine. So at the Big Bang, all of time, space, energy and matter was created. The universe is super dense and is super hot. So this is a fundamental principle of the hot Big Bang model. All of the universe was created in a super hot, super dense instant. Now after 10 to the minus 43 seconds, now this is very difficult to imagine as humans perceive an instant as 0.01 seconds, so you can't really imagine this particular time. The universe undergoes a super fast exponential expansion called inflation. So in this fraction of a second, the universe increases in size from the size of an atom to the size of a pineapple. Now the idea of inflation is a massively discussed principle in physics as whether it actually happened, but it's the only way for the mathematics of the Big Bang to work. So at inflation, the universe undergoes exponential expansion and the universe cools down when this happens. Now after 1 second, electrons, protons and neutrons form in the universe. It's still too hot for the particles to form atoms, however, because the universe is about 10 to the 11 degrees Celsius. Now charged particles such as electrons and protons prevent any electromagnetic radiation from being emitted, so the universe is pretty much a massive super hot fog. So as the universe cools down, as the universe expands, okay, it will continue to cool down and therefore subatomic particles will form. Now after 3 minutes, a rapidly cooling and expanding universe allows the neutrons and protons to clump together to make nuclei. Now at this point, electrons are still free in the universe. Now as at this point there's no such thing as electromagnetic waves, the universe is still dark, and this is known as the Cosmological Dark Age because you literally can't see anything because there's no waves of electromagnetic radiation. So at this point our nuclei have formed, so the matter and energy are still joined, so energy cannot flow throughout the universe. But after 300,000 years after the Big Bang, the electrons combine with the nuclei to form atoms. Now it's mostly 75% hydrogen and 25% helium formed in this new cool universe. Now at this point, electromagnetic radiation can finally shine, the fog is lifted, and this is the furthest back we can see in time, where the universe now has an average temperature of 10,000 degrees Celsius. So the universe has cooled so much and expanded so much that energy and matter have now decoupled, and this allows radiation to be emitted for the first time. Now this produces what we call the cosmological background radiation of the universe. Now this image can be found in all directions of the universe and has been extremely redshifted and has a peak temperature of 3 Kelvin. Now it's important to note that the cosmological background radiation can only have been formed in the Big Bang model. So whilst atoms have now formed, the temperature of the universe is still high enough for 25% of the hydrogen in the universe to fuse into helium, but these conditions are only present for a very short amount of time. So this is why the abundance of hydrogen and helium can only be explained by the Big Bang model, because you needed that higher temperature at the start of the universe to allow some hydrogen to fuse into helium. Now the cosmic microwave background is the universe aged at 300,000 years old. The red spots show areas of high temperature which later go on to become galaxies, and the blue spots show areas of low temperature. These later go on to become the voids of our universe. So this is the first ever electromagnetic radiation released into the universe. So it's the earliest possible picture of our universe. Now after 1 billion years, the hydrogen formed in clouds clumped together under gravity for the first time, so the first protostars and proto-galaxies are formed. So stars ignite for the first time, creating areas of high temperature, but the average temperature in the universe is now minus 200 degrees Celsius. So the density of our universe is now becoming extremely clumpy. There's areas of high density such as galaxies and areas of low density such as voids. So what we have now is our stars form in the first stellar cycle in the universe. Now interestingly, this forms massive stars which move quickly through the stellar cycle and implode via supernovae. Now the first stars die, spewing out the newly formed heavier elements in about 10 billion years after the Big Bang, such as carbon and oxygen in their deaths. So the process of new stars such as our sun and the solar system form again, and the universe continues to cool. So with the second stellar cycle, the universe has become even more clumpy. There are regions of galaxies and voids in our universe. So now we're at 13.7 billion years after the Big Bang, and this is the current universe. Many stars, galaxies and other objects have now formed. The universe has cooled to a chilly average temperature of minus 270 degrees Celsius, which is 3 degrees above absolute zero. So the universe now, we notice there's a greater density difference. We have areas of high mass, the galaxies, and areas of low mass, the voids. So we can show a timeline of the universe with the following graphic. So with the Big Bang model, it's the idea that we have a very hot, very dense universe at the start, but we then got a cold, much larger universe which is clumpy with areas of matter and areas of space 13.7 billion years after this fact. Now it's important to remember that the early universe was very hot, very dense and very uniform, and in addition the observable universe is very small when it is very young. Now there are 3 things needed for this scientific model such as the Big Bang theory to be accepted as the correct one. You need a testable idea, mathematical proof and experimental evidence. Now this is the same for every model in physics, even the Big Bang model. Now remember, a scientific model is a testable idea which explains a scientific concept. So if the model cannot explain the experimental data, the model must be replaced by one that does. So for the Big Bang model to be accepted, there must be evidence which can be explained by the Big Bang model and not the steady state model. So just to clarify, the idea of the Big Bang theory was provided by George Gamow in the 1950s. The mathematical proof of the Big Bang theory was provided by Stephen Hawking in the 1960s. However, where is our evidence for the Big Bang theory? Now it's important to note that redshift is proof of the expansion of the universe. Now this is accounted for in both the steady state theory and the Big Bang theory. This is because both methods state that the universe is expanding, because the Big Bang theory states that the expansion began at the start of a super dense, super hot universe, while the steady state theory indicates the expansion has occurred in an infinitely massive universe. So where is the experimental proof for the Big Bang theory? So, by the mid-1960s, physics was stuck. Hoyle had proven that steady-state theory could be possible, and Gamow and Hawking had done the same with the Big Bang theory. So neither theory had any evidence to show that either was the truth of reality, since redshift could be accounted for both theories, as both theories showed that the universe was expanding. Now, Hoyle had in fact stated, if all matter was created in the Big Bang, where was all of the energy? Like when a firework explodes, you can observe energy as heat and light. If all of the matter was created at one point, surely you would observe the aftermath of an explosion. All you see when you look into space is darkness. So Gamow and Hawking was stumped, because when you look into space you don't see an afterglow of energy from the Big Bang. Or do you? Because Hawking and Gamow were saved by a discovery from a remote telescope in New Jersey. So, working at the Bell Labs in New Jersey in 1964 were Arno Penzias and Robert Wilson, who were experimenting with a horn antenna originally built to detect radio waves bouncing off weather satellites. So, to measure these faint radio waves, they had to eliminate all recognizable interference from the receiver. So, they removed effects of radar and radio broadcasting and suppressed interference from the heat in the receiver itself. Now, when Penzias and Wilson reduced their data, they found a low, steady, mysterious noise that persisted in their receiver, and this is a picture of the data that they received. Now, this residual noise was 100 times more intense than they expected and was evenly spread out over the sky and was present night or day. Now, they were certain that the radiation did not come from the Earth or the Sun or even our galaxy. Now, this radiation was interfering with the results that they wished to measure. So it was interfering in the microwave spectrum of the electromagnetic spectrum. So it was a very important idea. Now, after thoroughly checking their equipment, removing some pigeons nesting in the antenna and cleaning out the accumulated drop-ins, this noise remained. Now, both concluded that this noise was coming from outside our own galaxy, though they weren't aware of any microwave sources that could account for it. So what source was present everywhere in the universe which produced these microwaves? So it was finally reasoned that the Big Bang in the Big Bang theory must have scattered not only matter that condensed into galaxies, but also released a tremendous blast of radiation. Now, without the proper instrumentation, this radiation would never have been detected, but it was with Penzias and Wilson's antennae when we had that suitable equipment. Now, just again to remember, the Big Bang was not an explosion, however, there's just no other way to visualize this idea. Now, the Big Bang released this radiation about 300,000 years after the initial point of formation, because before then, like mentioned before, electromagnetic waves were trapped by matter. So it was realized that the radiation was originally released by the Big Bang as gamma waves 300,000 years after the point of creation. This is because gamma radiation is the most energetic electromagnetic waves. However, this couldn't be the microwave signal observed by Penzias and Wilson, or could it? Well, yes, it actually was, because originally these gamma waves were released 300,000 years after the Big Bang, but as the universe has expanded, the wavelength of these waves has increased. This is redshift, so this has turned the gamma waves into microwaves, and we can observe this microwave radiation from anywhere on Earth when pointed towards space. This is the evidence which proved the Big Bang theory. So this is called the cosmic microwave background, and this is because it was found everywhere in space in the microwave background. So again, this is the evidence that proved the Big Bang theory, because in millions of years the cosmic radio wave background will replace the cosmic microwave background, because our wave will continue to expand with our universe and it will expand into the radio spectrum. Now, interestingly, this is why space is not at absolute zero, it's at 3 degrees above absolute zero, because it's being slightly heated by the cosmic microwave background. So it's interesting to think that the fabric of reality is still being heated by the afterglow of the Big Bang. So everywhere we look in the universe, we observe radiation from the universe itself. Now, this is the energetic emission from the Big Bang, which we call the cosmic microwave background. Now, it was originally a very short, very high intensity electromagnetic wave emitted shortly after the Big Bang, but over time the wave has stretched out into the microwave as the universe has expanded, which is what we observe today as a microwave, and this is evidence for the Big Bang model of cosmology. So you can see here the observation of a microwave telescope taken in the cosmic microwave background. Now remember, it's the same in all directions, showing it must have originated from a single starting event of creation. So the cosmic microwave background, or CMB, is one of the most important discoveries ever made by humanity, as it gave us proof that the universe was created by a Big Bang. So this is a picture of the universe aged 380,000 years old. It's the earliest possible picture of the universe. Now, according to traditional physics, the CMB should be constant. However, quantum mechanics cause fluctuations of the CMB, which makes the universe uneven and not even density when the universe was very small. So the areas of high density in the CMB went on to form galaxies, and areas of low density in the CMB went on to form voids. And again, this was the experimental proof of the Big Bang. Now, all models in science need to be able to explain experimental results and evidence. So the steady state model could not explain the CMB, so we went with the Big Bang model. So what have we learned in today's lesson? Observed redshift provides evidence that space itself is expanding and supports the Big Bang theory. The Big Bang theory suggests that the universe began from a very small region that was extremely hot and dense, and students should be able to explain how redshift proves evidence for the Big Bang model, and how scientists are able to use observations to arrive at theories such as the Big Bang theory. So if we have been successful and learnt in today's lesson, we should be able to understand what the Big Bang theory is, understand how the universe has changed over time, and understand what the steady state theory is and compare it to the Big Bang theory. So I hope you've enjoyed today's lesson on the Big Bang theory, which is part of the space physics topic in GCSE Separate Science Physics. Thank you very much for watching, and have a lovely day.